Our nation's economy depends upon income-producing vehicles of all types and various modes of transportation. All of these applications are powered by either gasoline or diesel engines. To get these engines started whenever and as often as desired is the job of heavy-duty batteries. Heavy-duty batteries are frequently discussed, but seldom understood. You need to know what can cause premature battery wear-out and how to make the necessary connections. Later on, we'll be discussing the major causes of premature battery wear-out and some simple maintenance checks to spot sources of trouble. In this presentation, we shall look at the two major types of batteries used in heavy-duty vehicles: the conventional or old-style battery and the maintenance-free battery. The maintenance-free battery incorporates design features which are different from old-style batteries. These features eliminate many of the causes of early battery failure. Right now, let's look at only the old-style batteries. This type of battery is used as a source of electrical power on literally millions of vehicles. It is used to supply power to the cranking motor and also to the accessories when the engine is not running and when accessory load exceeds the generator's output. Let's build up a simple battery and see how it works. The most basic part of the conventional battery is the flat metal grid, which is made of lead antimony alloy. Remember these words, lead antimony, because later on we'll see that a different grid has been developed which does not use antimony. The grids are pasted with active material to form negative and positive plates. Charged negative plates contain sponge lead, and charged positive plates contain lead dioxide. The plates are kept apart by a microporous separator. A simple basic battery is formed when the two plates and separator are placed in a solution of sulfuric acid and water called electrolyte. Due to the chemical reaction between the electrolyte and the two dissimilar plates, an electrical pressure or voltage exists between the two plates. When the simple battery is connected to a 2-volt bulb, current flows throughout the circuit. The two plates, the electrolyte, the highly porous separator, and the bulb form the complete circuit. Thus, when the bulb is lit, current is flowing in the circuit and the battery is converting chemical energy into electrical energy. As the current continues with time, the acid in the electrolyte combines with the active material and forms lead sulfate in both plates, and they become more chemically similar. Also, water is chemically formed in the electrolyte, and the electrolyte becomes weaker. With similar plates immersed in a weak electrolyte solution, our basic battery is discharged or run down and can no longer supply current to the bulb. The battery can be restored to its full state of charge by forcing current in the opposite direction to that during discharge. This is one of the jobs of the generator or alternator, namely, to provide current to charge the battery. To summarize, we have looked at a simple basic battery and have seen that a chemical reaction occurs during discharging to provide electric current. Also, the chemical reaction reverses when the generator or alternator provides current to charge the battery. We're now ready to see how an old-style battery is constructed. An element is made by stacking a negative plate, separator, positive plate, separator, negative plate, and so on, up to the number of plates needed. Then comes the welding or lead burning of the similar plates to a lead casting, called a plate strap. Thus, positive and negative plates alternate and are kept apart by separators. Without these separators, the plates would touch and cause a short circuit. The element still produces only 2 volts, but the current capacity increases as more plates are used. The discharge current capacity, measured in amperes over a period of time, is a function of a number of plates in each element, the amount of sponge lead and lead dioxide in the plates, and the type of separator material. When a heavy lead connector is used to connect the positive plates of one element to the negative plates of another, and 3 elements are used, a 6-volt battery is formed. If 6 elements are used, the total voltage is 12, thus a 12-volt battery. The current capacity is the same as in one element, but the voltage has been increased to 12. Let's look at the construction of this battery. The case is made of a hard rubber compound for added strength. It is resistant to vibration damage and will not react chemically with the electrolyte. The case is divided into 3 cells by partitions. The 3 elements are assembled into the 3 cells. During the life of the battery, it is normal during charging and regular use for part of the active plate material to shed and fall to the bottom of the case. Most of this shed is usually positive material. The elements rest on bridges or supports, forming sediment chambers in the bottom of each cell to collect any active material shed from the plates. Without sediment chambers, the plate material would short across the bottom of the plates, causing premature battery failure. Each cell is sealed with a cover, and the elements or cells are connected over the partition. Then electrolyte is added. This will be discussed in a few moments. With the covers and cell connectors in place, a sealing compound is added to complete the battery. When installed in the vehicle, the battery retainer should be torqued to the vehicle manufacturer's recommendation. Delco batteries have flame arrestor vent caps. These caps, when tightly assembled, appear to form an airtight seal, but actually the filter in the center of the cap is porous. Gases can exit from the battery through the porous filter, but a spark or flame cannot enter. Now that we have seen the major construction features of the conventional or old-style battery, let's look more closely at the electrolyte. A typical electrolyte solution by volume would be 64% water and 36% pure sulfuric acid. The resulting mixture has a specific gravity of 1270. This means that the electrolyte weighs 1.270 times as much as an equal volume of water. We have seen as the battery discharges, the electrolyte approaches but never quite reaches pure water. Using a hydrometer, electrolyte can be drawn into its barrel so that the float measures the specific gravity. The float must be suspended freely in the liquid to obtain an accurate reading. In this manner, the state of charge of the battery can be determined from the specific gravity reading. Specific gravity readings are affected by temperature. A battery is considered to be at full charge when the specific gravity is close to 1270 at 80 degrees Fahrenheit electrolyte temperature. Specific gravity readings taken at electrolyte temperatures above or below 80 degrees Fahrenheit must be corrected to compensate for the effects of temperature. To determine the state of charge, we need to know what the gravity reading would be at 80 degrees Fahrenheit electrolyte temperature. To determine this, simply add 4 points to the reading for every 10 degrees above 80 degrees Fahrenheit, or subtract 4 points from the reading for every 10 degrees below 80 degrees Fahrenheit. To illustrate further, place a thermometer into the electrolyte to measure the exact temperature. If the temperature is 0 degrees Fahrenheit and the reading 1232, the gravity corrected to 80 degrees Fahrenheit is 1200. Thus, the true state of charge, 1200, is much less than is indicated by the hydrometer reading of 1232. Whenever the battery is charged, some water will be lost due to the gassing. By removing the vent caps and looking into the battery, the electrolyte level can be visually observed. If the level is low, there will be no visible distortion at the split ring at the bottom of the vent well. However, if the level is okay, the electrolyte level will appear distorted at the split ring. Since it's normal for an old-style battery to use some water during its life, the vent cap should be removed periodically and clear, clean water added as needed. If available, distilled water should be used. It is very important to maintain the electrolyte at the proper level for maximum battery life. Never add electrolyte to a battery already in service. The relationship between specific gravity and electrolyte freezing temperature should be carefully observed. Note that there is never any danger of electrolyte freezing if the battery is fully charged. But if the specific gravity drops to 1160, the electrolyte will freeze at 0 degrees Fahrenheit. Obviously, freezing can occur if precautions are not taken, and battery damage will result. During charging, we have seen that some water usage is normal, as some of the water in the electrolyte will change into small amounts of hydrogen and oxygen gases. These gases, which are highly explosive, escape to the atmosphere. Care must be taken to prevent sparks or flame from igniting the gases. As hydrogen and oxygen gases leave the battery, some of the sulfuric acid may also escape to the atmosphere. Since acid is highly corrosive, always avoid contact to the body and clothing. If contact is made, flush immediately with large amounts of water to neutralize the acid. Always shield eyes when working with batteries. We have finished our discussion of electrolyte and will now turn our attention to battery charging. Chargers which convert 110 volts AC down to a low DC voltage are commercially available to charge run-down batteries. Be sure to follow charger manufacturer's procedures when using his charger. Before charging, check the electrolyte level. If below the plates, add clean, clear water, enough to just bring level to above the tops of the separators. After charging, add drinking water if needed to bring electrolyte level up to the split ring. Always turn off a charger before connecting to a battery. Then be sure to connect positive to positive and negative to negative. Before disconnecting, turn off the charger. As a general rule, any battery may be charged at any rate as long as spewing of electrolyte does not occur, or for as long as the battery temperature does not exceed 125 degrees Fahrenheit. Many chargers have a timer to minimize the chance of causing battery damage. The best way to bring a battery to a completely full state of charge is with the slow charge method. Charging rates in the 5 to 10 ampere range and periods of several hours may be required. The battery is fully charged when over a 2-hour period no significant change in specific gravity appears. Normally, a fast boost charge is used to bring a battery to a state of charge suitable for testing or cranking the engine. It may be used before placing the battery into service. It is assumed the vehicle operation will be such that the alternator will completely recharge the battery in a reasonably short period of time. Fast charge rates of 30 amperes or above are common, and charging times must be limited to 1 or 2 hours. Fast charging, followed by slow charging, will usually bring a battery to a full state of charge. To review our study of old-style batteries so far, we have covered 1. Theory of operation, 2. Construction features, 3. Electrolyte characteristics, and 4. Charging. Each battery is designed for a specific application or capacity and is rated accordingly. Batteries are rated by 2 methods. Reserve capacity is the time in minutes it takes to reach a terminal voltage equal to 1.75 volts per cell while being discharged at 25 amperes at a battery temperature of 80 degrees Fahrenheit. This rating is a measure of the time it is possible to travel in a vehicle at night with minimum electrical load and no generator output. The cold cranking amps at 0 degrees Fahrenheit is the maximum amperes maintained for 30 seconds with terminal voltage equal to or above 1.2 volts per cell. 1.2 volts per cell represents the minimum voltage at 0 degrees Fahrenheit capable of cranking the engine. The major factors that can cause early failure of old-style batteries will now be discussed separately. These factors are 1. Undercharging, 2. Overcharging, 3. Improper electrolyte level, 4. Cycling, and 5. Vibration. In heavy-duty applications, corrosion at the battery terminals results in most cranking problems. These batteries do not get fully charged and consequently fail to crank. During discharge, we have seen that sulfate forms in the plates. If a battery in a discharged condition is allowed to remain undercharged for extended periods, the plates will become dense, hard, and chemically irreversible. Shortened battery life will result. Also, the lowered specific gravity makes the battery more susceptible to freezing. In the case of adding too much water, overfilling, loss of electrolyte will occur as the battery is being charged. Not only heavy corrosion can occur on the cable clamp connectors and the posts, but also the electrolyte is diluted, with resulting loss in battery capacity. Overcharging in old-style batteries forms hydrogen and oxygen gases, which cause oxidation of the positive plate grids. Oxidation causes the grids to crumble, resulting in early failure. If the electrolyte level is allowed to drop below the top of the plates, the plate material exposed to the air will harden and become chemically inactive. The battery, in effect, becomes smaller. It will be overworked, and its life will be shortened. Add only cleared water or distilled water. Any contaminants in the water will also shorten battery life. A battery cycle consists of a deep discharge and recharge. Cycling causes the positive plate material to shed from the grid and fall to the bottom of the battery case. Again, loss of capacity occurs and early failure results. Cycling results when the vehicle has high electrical loads and either spends a lot of time in slow-speed operation or does not have enough alternator capacity. Damaging vibration can occur on some applications, and high-speed cameras can show that the battery is actually vibrating or being shaken severely. The battery case may crack, and the plates and separators may be damaged to the point where the battery may fail completely. Proper battery selection and secure hold-downs for the application are essential for satisfactory life. Improved mounting locations and proper battery capacity recommendations for heavy-duty diesel trucks are further covered by the regular Common Carrier Conference recommended practices. Now that we have discussed battery fundamentals, rating, and modes of failure, we're ready to discuss testing the heavy-duty battery. Multiple batteries must be disconnected from each other before performing a battery test. Disconnect the ground connections first. After disconnecting each battery, there are 3 steps to follow to determine if the battery is worth reusing. 1, a visual inspection. 2, a hydrometer check. 3, a load test. The visual inspection is just as important as the other 2 steps. Check the posts to see if they're loose. Look for cracks in the case, or add water if needed. Clean, clear water should be used and fill cells to just under the split ring. If water was added, then charge the battery for 15 minutes at 15 to 25 amps to mix the water with the electrolyte before checking with a hydrometer. Next, when using the hydrometer, carefully insert the probe into the cell so as not to damage the top of the plates. Check the specific gravity of each cell and note the highest and lowest cell reading. A variation of more than 50 points means the battery has lost capacity and should be replaced. If any cell reading was less than 1200, the battery must be charged until all cells are over 1200. If the battery cells read over 1200 specific gravity, connect a carbon pile or battery load tester across the battery terminals as shown. Be sure the load is off. Connect a voltmeter across the battery terminals also. Always follow the specific directions of the battery load tester manufacturer. If the battery was boost charged, apply a load of 300 amperes for 15 seconds. This will remove the surface charge caused by gassing action during charging. Wait 15 seconds for the battery to recover or stabilize before proceeding to the next test. Since we are testing a Group 4 6-volt battery, the load we are after is 450 amperes. Apply the 450 ampere load for 15 seconds and observe the voltage. At the end of 15 seconds, the voltage reading should be holding steady at or above 4.8 volts. Does temperature affect the battery? Sure it does. So if the battery electrolyte is cold, a lower voltage reading is normal. Following these steps will provide the best possible knowledge that you have only good batteries installed. Returning a battery to service without eliminating potential causes of failure almost assures early failures. After a battery passes the testing, what should you do? First, clean the battery posts thoroughly with a wire brush or a suitable cleaning tool to ensure good metal-to-metal contact. To remove dirt and corrosion, scrub the battery with a solution of water and baking soda, using a ½ pound of baking soda to 1 gallon of clean water. Be sure the vent caps are in place so the solution does not enter the cells. Then, rinse with clear water. The use of high-pressure hoses or steam is not recommended, since it will force contaminants into the cells and could also remove battery labels. After being cleaned, fully charge the batteries before returning them to service. Charge until the specific gravity does not change significantly for 3 one-hour interval checks. Check the batteries regularly to prevent electrolyte spewing or excessive temperatures. After turning off the charger and disconnecting it, check the electrolyte level and add water if necessary. Install vent caps securely. The batteries are now ready for service or storage. Old-style lead antimony batteries self-discharge when not in use for long periods. After removing the batteries from the vehicle, clean the cable clamps with a wire brush and also clean out the battery box. box and hold down with a solution of baking soda and water, as already discussed. Then rinse the battery box and hold down with clear water. After installing the batteries and securing the cables, use a protective coating of grease or petroleum jelly over the clamps. Ensure that the battery box is secure and all hold downs can be securely fastened. Torque the hold down to the specified values. This family of heavy-duty batteries has been the backbone of the electrical system over the years. However, as technology is developed, better ways are found to reduce costs, improve performance, and eliminate many of the maintenance needs just discussed. This will be discussed in part 2 of this program.